Alrighty, thank you everyone for coming back. We have a few more presentations left, and I can assure you they are going to be fantastic. So, thank you for sticking with us. Our next presentation is going to be a great combination between two wonderful speakers from the University of Queensland Sustainable Mineral Institute, Dr. Tom Evans and Dr. Pascal Bolz. Firstly, Tom is a geologist with over 20 years experience in the mining, exploration, and resource sectors. He's worked extensively in the Northwest Mineral Province in exploration, business development roles, predominantly focused on finding and developing copper resources. Secondly, Pascal is a geologist by training and now works as a geospatial analyst. He specializes in regional planning for mining regions in transition, as well as landscape scale erosional monitoring and modeling. His work supports the mining industry, governments, and regional stakeholders with practical data-driven tools to guide decision-making. Today, they will be co-presenting on tectono-economic modeling for the next 25 years of copper production in the Northwest Mineral Province. Please join me in welcoming both Dr. Tom Evans and Dr. Pascal Bolz.
Thanks, Janelle. This project is really part of a larger alliance between the department and the SMI, looking at critical minerals and circular economy research as part of the alliance. We call it DORA, Department of Resource Alliance, just to keep it nice and short. There's an abundance of other projects that have been funded over the last year and will be funded to the coming year. Copper futures, modeling the next 25 years of copper production in Queensland's Northwest Mineral Province, a new foundation for policy development and infrastructure planning. It's a big piece with a big team behind it. You see here just the project leads, the individual sub-disciplines presented. It spans over environment. We have a social scientist involved. We have resource geologists. We have an economist here, one with doing fantastic work. We need a geographer like me, a guy who can map and access Queensland's fantastic spatial data and put it into context. So this is a whole new approach, big piece of research. How we think about unlocking a region at large scale that is in a very turmoil, tremendous transition. Before we look into the future, let's look back a little bit. On this chart here, we can see the development of copper production and for Queensland, for Australia, and the copper commodity price. You can see the drama unfolding there in the early 2000s. Copper price is shooting up around 2005, 6, and in the meantime, copper production in Queensland has been already on a steady decline prior to this massive price drop. National production at best is running sideways during that period, but it's also on a slight decline. The way we have been mining copper in the Northwest Mineral Province has been focused on small number, very large deposits. We have mined 12 million tons of copper that we produce in the Northwest Mineral Province, with 80% coming out of Mount Isa and Ernst Henry alone. The other significant producers such as Osborne, Eloise, and Capricorn, but you can see based on the size of the bubble, their deposit size is much smaller. So this moving forward requires a completely different approach. Just the next map I'm going to show you shows basically what's left on the ground and how it is distributed. So you can see the very large mega deposits that exhausted. The Mount Isa copper mine as close, but it's closing. Close this here, and the region faces challenges because the infrastructure is not there, or you need to assess the infrastructure. to see how we can unlock actually copper deposits and spatially more dispersed picture. So, problems with existing mines reaching the end of the life. We have new mines under construction currently, such as Eva and Jericho, and there's about 10 million tons of copper contained in 28 different resources. We have projects in place that are aiming to mine roughly a third of those 10 million. The question is now, can we come up with a plan to unlock the rest? And this is why I'm handing over to Tom. I had 2 more slides. Cool. So, what is it that we're doing here? We're building a techno-economic model of copper production in Queensland that covers the next 25 years of production. So, I guess the first question is, what's a techno-economic model? So, we've got a nice definition on the screen there. It's a model that evaluates the economic viability and performance of a complex system of interrelated processes. And that's what we have here. And this is a temporal-spatial model. So, we're looking at things that are distributed across a map and happening across time, starting and finishing at different periods of time. So we need to incorporate all of these aspects into this model and into how we structure this model. So things, we need to look at copper deposits, where these resources are, where the active mines are, where the processing facilities, refining and smelting facilities are, and what the transport infrastructure that links all of those things together looks like, in addition to other things like all of the input costs that go into this: water, power, etc. So, what do we get out of this model? Well, this model, the main outputs that we produce is how much copper is going to come out of the region, how much mine waste will produce, what the potential power and water requirements to produce that material are, and what the infrastructure requirements and utilisation will be, and things like how much royalties will be generated going forward for planning. So these are the sort of things that we're looking to generate from this model. But importantly, so I'll step back a little bit. This is talking predominantly about phase 1 of this project, where we're doing a base case scenario. We're looking at a baseline of copper production from mines that are currently going, mines that we know are going to be in train. And we're just leaving out things that may go ahead, may not go ahead for the time being. Phase 2, which we're starting, we're going to look at scenario modelling for different things. And Pascal will talk a little bit about the different options that we're looking at modelling later on. So the first part of this model is building the supply chain network structure for the model. So the model is based, as you can see, on this on a supply chain network for copper. On the right-hand side there, we've got a non-spatial representation of that supply chain. You can see we have deposits and mines. The first column, they produce ore. That ore is then transported by these little transport transport routes, connectors to refining and processing nodes. And then, so ore gets turned into concentrate there, or if it's an SX-EW plant, gets turned into cathode copper. And then that product, the concentrate, will go to a smelter, which then gets transported as copper, anode copper to a refinery, turned into cathode copper, added water townsville. And so that's how it is. Each of these points has inputs, whether it's ore, and outputs. If it's a mine, it's inputs to ore, outputs to concentrate. And each of these transport nodes is it's either a railway, track, a road, and we know the distance between each of these, and we've got a rough cost of dollars per tonne per kilometre that we can plug into these to inform the model. And each of the connector nodes are really determined by the mapping that you can see on the left, and each one is defined for each project linkage and each node. So in building the economic model, you can see we've taken that broad architecture for the supply chain network, and Brian has built an economic model around that. And I'm not going to try and explain the workings of the economic model. Suffice to say, my best understanding is that what we have is a series of discounted cash flow models that are all
basically linked together in a way and nested within large blocks of Python code. So this is a much better descriptor of how the model works than the blocks of Python code, but if you want to see what the model looks like, it looks like Python. But what comes out of that model is firstly we look at base and copper production from this phase one base case scenario. And so looking at the mines that we think are going to be producing over the next 25 years, we're looking at 430 million tonnes of mined ore, producing about 3.3 million tonnes of copper, as Pascal mentioned before. That's roughly a third of the known resources of 10 million tonnes that are currently in job resources in the ground in the North West Minerals province. Also, 2.8 million ounces of gold produced. One thing you'll notice there's a big ramp up at the start of the chart. That's EVA coming online, and then a steady decay, then a big drop off, and Ernest Henry is due to finish around in the early 2040s. So that's when the resources currently quoted and published by Evolution is depleted, being mined at the current rate of about 6.5 million tonnes that it's been mined at. We expect that resource to be increased in size between now and 2040, but there's obviously more challenges associated with mining that ore body deeper and deeper. They haven't found the bottom of it yet. Another thing to note on this chart is the EVA plant that we've modelled in here is 12 million tonnes per annum. That's what they put, what Harmony's put in their documents. I think they subsequently said that increasing that to 18 million tonnes per annum. So that'll significantly increase the production there in that 25-year period. But as you can see, you know, we're still at around about that. We're looking at about 200, up to about 200,000 tonnes of copper a year. Is that right? Get the numbers. At maximum, and then declining down again. So looking at some of the preliminary results from the economic modelling that the ones output from here, we've got some cost structure and profitability of the mining operations, and you can see the quick takeaways from this chart. Firstly, having this cost structure for each of these operations is really important for phase two of this modelling. We can see how different model scenarios will impact potentially the profitability of different aspects of the cost structure of each operation on a case-by-case basis. But looking at these, I think the key takeaway you see from here is that Ernest Henry, the gold credits at Ernest Henry basically pay for the mining, and the copper is credited on the copper, which is nice for them. You can see the EVA operation on the far left-hand side there. Very low cost because it's an open pit operation with very high tonnage throughput rates. So lots of economies of scale there. On the far right, Mount Kelly, which is hub and spoke SXW operation, so they're trucking ore from external mines to a central processing hub. They've got much higher transport costs in their cost structure than any of the other operations. So now I'll hand over to Pascal and wrap it up.
So basically, Tom showed the results of the economic analysis, and now we need to start thinking about stage two. And we're going to refine the techno-economic model. And I think it's really important to understand a couple of cornerstones, a couple of issues in the region that could actually drive scenarios going forward in this project. There's insecurity around and access around power prices. There's multiple scenarios I could imagine. A site could connect to the Northwest power system, and because operators in the region, they have the choice. A lot of operators are thinking about off-grid solution, but we're not thinking about a wind farm and these things. Water supply challenge, massive in the region. There's a reliance on groundwater and very high uncertainties throughout groundwater in the regions, particularly outside the Greater TV Basin. The transport infrastructure probably requires upgrades to improve resilience against weather events, flooding and high maximum temperatures, specifically for the rail, as soon as there's flooding in the area. basically cutting that rail corridor. With multiple instances of those events in the past. These factors are collectively driving up cost for infrastructure services, affecting the economics of these mining projects. Brief overview of what the other teams in environment and social and governance found. Most deposits that we sort of looked at, I think, group of 20, 25 deposits in total, or 28? 28, yeah, that's right. So we created spatial overlays to sort of look, okay, what are potential heritage environmental issues that might occur. And because there's such a lot of mining history, oftentimes there's more environmental overlays in this area, at least not for the immediate deposit. Questions what happens sort of in proximity around. There are site-specific environmental risks that remain. You can see it here on the map, we overlay with the flood model. There's deposits, mines that are affected by flooding, A&D, there might be wildlife habitats around, and these will require mitigation strategies, which in the end will cost money and have to be factored in to an economic model. The social team actually found that the community analyzer, they actually went out and structured interviews with stakeholders in the region, and a lot of their findings are resonating with our findings around the infrastructure. A big concern about cost for energy, transport, and water, and yeah, the communities are really concerned about this transitional period that we're in right now in that regard. So we're currently in deep into scoping stage 2. We want to take a closer look at what is the most bang for buck, literally in our economic model, looking into sensitivities of the economic model and how can we leverage the databases that we have already created in stage 1 to now go outside of these 6 mines and deposits and see how quickly can we generate data for these 28 other or 22 other deposits. So that's the first point, incorporating more deposits into the supply chain network. We could simulate smelter shutdown or replacement scenarios. We're thinking about integrating power price scenarios, connecting to the national energy market by a copper stream down the line, maybe in 10 years. So that's sort of in the timelines that we're considering. Or connecting to the Northwest Power System, wherever that is an option, or even off-grid solution. How much would that cost an operator? We need to think about water access scenarios and specific unit prices. So we're probably going to have large error bars from them, but we need to incorporate this. The other thing, we're thinking about a new spatially optimized multi-user facilities for transport or processing hub. We can integrate into the spatial database and the next step into the economic model. There will be remote model refinements, revisiting copper production profiles, refine our findings of waste rock and tailings production, play with some copper price scenarios for the next 25 years, and a more detailed estimate of capital and operating cost, as well as inclusion of additional products. That's it from our side, and we're looking forward to your questions or discussions afterwards if we run out of time. Thank you.
Thank you, Pascal and Tom. Do we have any questions?
Well, what about mineralogy? You've sort of closed that out of the story.
So
I'm under the impression, rightly or wrongly, that there's still a hell of a lot of copper. It's deep, and it's a cost decision that it's closed. And if we start mining with robots or your AI and all that, maybe that would turn the whole thing around.
oh, absolutely, there's no question there's still many million tonnes of copper left underground at Mount Isa. The base case scenario that we looked at was only on, sorry, the base case scenario we looked at was only on mines that are currently operating or are basically in construction. So we didn't include Capricorn Copper, which is currently on care and maintenance due to environmental things. We haven't included Swan, which there's no plan, even though it's one of the largest undeveloped resources, in the country. But these are things that we're going to look at in phase 2, Mount Isa is a challenging one because even getting a mine started there would be open cut, say they could access some of that scenario, oxidised mixed commodity, or there's going to be a lot of issues around dust and what have you, production that close to town. But these are all things that we are scoping for the phase two, absolutely.
Any other questions? Wonderful. All right. Thank you, Tom and Pascal. Our next presentation is going to be given by Dr. Melissa Duque, a research scientist from CSIRO in Kerr. A geologist and a civil engineer with more than 15 years of industry experience, she has strong interest in rock characterization, particularly in geomechanics, underground fluid circulation, and rock fluid interactions. Recently, she has been investigating gas migration through faults, fractures, and complex interbedded rocks, as well as hydrogen generation and CO2 sequestration processes. She has flown in all the way from Perth to be with us today, so please join me in welcoming Dr. Melissa Duque.
Yes, thank you very much. So I'm back this afternoon to present a project overview on the GSQ-CSIRO network hydrogen prospectivity study. And I'm doing that on behalf of our project leader, Emma Brady, and also the whole project team. I'd like to begin by acknowledging the various Indigenous people of Australia, as traditional owners of the land on which we meet today, and pay my respect to the elders past and present. So in terms of the project team, we are very lucky. So the CSIRO side, we are partnering with the team. We have a bunch of different expertise that we deploy to this project to try to address the many different challenges we have, and we're going to see through the slides. We're also very lucky to have the GSQ side, a very active team, Janelle, Tony, and many others, including from the Solution Data Center, that have been helping us throughout this project. And also have an external advisory committee, and their role is really to guide us, to review our methodology, to review our outcomes, make sure that we are doing the best we can with the available resources. So what's the goal here for this project? Is to, I would say, minimally assess and whenever possible quantify the natural hydrogen prospectivity of Queensland on a state scale. So how we are doing this? We are doing this by deploying a holistic approach that integrates concepts and data sets from conventional and unconventional oil and gas exploration and production resources or data sets, or you keep in here high play focus. We also integrate mineral systems exploration and geothermal systems and groundwater systems data sets. The picture you always see is the main steps that we have defined following to build the outcomes for this project. And then on the next slide, we're going to go through these various steps briefly. So we start with our conceptual framework. So the idea is that we need to build a natural hydrogen system conceptual model to guide our thinking to the project. And this is done based on literature review, trying to collect all the data is out there from a petroleum perspective, from a mining perspective, from a natural hydrogen system perspective. On the picture, you can see the integration of all the main elements that we would expect to be present in a given natural hydrogen system. We see the various generation processes that could be playing a role here, from simple processes like oxidation of iron-rich rocks by the injection of water underground to manipulation of organic-rich rocks or primordial sources. And you also see other elements like the folks that want to be responsible for getting the water down to the formation in which you can have the hydrogen be generated. So, and many others. All right, so step two of our project is what we call the screening. So here, the idea is to go through the existing data set and try to highlight areas of increased hydrogen generation potential. When we do that, we're not excluding areas, we are trying to focus on the areas where are more promising in terms of generation. And we do that again by integrating various data sets, in various generation processes, the ones we mentioned in the previous slide, and we do that and create some regional maps that are going to guide us for solution focus. The result of this screening, which is complete, was that we defined 3 potential areas for this study. Again, it's highlighting areas of potential interest, not excluding any areas, but we decided to go with the other way, more eyes and bounce around, and then use some of the areas you can see in the figure as well. Step 3 is to design a prospectivity workflow. So the idea is to develop a GIS-based methodology in which we integrate various data sets for the hydrogen system elements. We define what we call input mappable layers for each of those hydrogen elements. We then apply a weight, a mineral weight, considering importance, the applicability of the competence of the data set that we are considering. Then we go to the generation of the prospectivity heat maps, considering the presence of salt of hydrogen, the migration pathways, and the trap. Then we apply the workflow that has been developed with the whole project team and all involved in the project to each of the areas that we are studying and generate what we call the prospective heat maps. Now, we don't stop there. We go and create another layer, which is called incorporation uncertainty on our data. So basically, what we're doing is considering what is uncertainty for our data coverage, what is uncertainty related to data interpretation for each of those layers that we are dealing with. And then we add this uncertainty on top of the prospectivity heat map that we just generated. And that's our final prospectivity map. Then we're going to categorization. Basically, we're going to now get the outcome of the workflow, which is the prospectivity maps, and we're going to categorize them based on notable data, low perspective, or perspective, but have a low to fair data coverage or high data confidence in that prospectivity map. And then one thing that we are doing differently in this project, one new thing from previous natural hydrogen prospectivity studies worldwide, is that we are doing an automation process. Basically, what we're doing is having some of our team members sitting together with the ones that are doing the prospective work and trying to take note of all the steps and participate in that so that their steps can go to our code for automation. What we get into that with that is that if tomorrow, after the project is delivered, the data set is given to the community. If new data sets come available, they can be incorporated into the workflow and then new prospectivity maps can be generated. Another step that we have in this project is the potential of new data sets. So here the idea is, so besides all these data sets that are currently available, besides all these modeling reports that I just mentioned, we're going to try to generate new data. So new data in many ways. So one way is to, for instance, using machine learning and AI-based test data search algorithms to extract and compile any hidden information that might be there in reports and tables that could be a clue for hydrogen occurrence. And also the analytical investigation of legacy core, as I mentioned this morning, in the reports that are out there. So the idea here is that we go choose some type information from different study areas. We analyze those rocks and try to answer if there is value migration of hydrogen has ever circulated in salts, or if these salts have some potential for hydrogen generation by oxidation today. So we do this by doing a quick screening, a sample selection. We do some techniques that we develop, GSQ-CSIRO, so machine, we do scan techniques like the gamma spectroscopy, to analyze through diffusions. Also do soft rock characterization for whole rocks chemistry association, and we go and do some very custom workflow that we develop to investigate what is the potential of rocks to generate natural hydrogen through oxidation. So we are here with this project. So the screening, as I mentioned, is complete. All the areas of interest have been defined. So the GIS-based workflow has been developed as well. We are right now on the waiting stage and next couple of weeks. The main activities, although as I mentioned, they are all going parallel. So we have delivered today a number of reports, including some advice to government in terms of what is the international landscape for natural hydrogen energy in relevance of the information to Queensland. We have delivered reports on the methodologies, different sections of the project and the conceptual model. We're also working on techno-economic analysis as well. So this project, we have a few workshops between GSQ and CSIRO to keep, we all align what we are doing, how we progress in the case we needed. So, this four have happened already, and we'll have two more, next year. And, this project is due to be concluded by the end of this financial year, and expected report should be out there around May. And I will stop here. Thank you for your attention.
I just have a question about the ore formation. I don't know anything about hydrogen deposits. You need what? Is it like petrol, oil and gas?
So it's yes and no. So there's different ways that people are looking into natural hydrogen. So here, natural hydrogen is basically hydrogen is produced presently naturally by earth on the ground over the years, right? So then we fit in there as a combination of theory or in or not, it's what discussion around it. And then when you do it to the surface, depending on if it's located from the perspective, if it's located from the perspective or both. So we have the mining case, which is the only case in the whole that we have production of natural hydrogen, and use of that for community, the maintenance for community. And what we try to do is make sure that when we are trying to understand exploration prospectivity, implementing all those factors from the target mining.
I'm just wondering, you've got hydrogen, what about helium? Also, people for that, I mean, that must be a strategic element as well, I just really is that.
Yeah, I think we all had about, for most of the people kind of about the association between natural hydrogen and helium. We have the South Australia cases that are quite hot at the moment, and another place in the world. And yes, it is normal to have the dual occurrence. Also in this.
If you've got hydrogen coming out of the ground, how do you know it's hydrogen? How do you test for it? Test for it. How do you know what the gas is?
So we can actually look into our volume of fluid and see what is that, right? So what it would be, so we can sample on the ground, we collect samples, so we can send it out and classify what's.
Okay, but how do I do it? What a match, Kerr.
Don't sit there.
There's a lot of gas wells in southwest Queensland. There's methane, natural gas. Is there not hydrogen mixed up in that?
I don't know about those, and these I can tell you, can report on a few, even the lab, we try to simulate next hydrogen for oxidation of iron rocks. It's common to get methane as well.
But it seems to me there'd be a lot of drill holes in the Great Artesian Basin that there must be assay information here. I couldn't, in the petroleum industry, to tell you where the good places were.
I think that's a good reason to keep working on those data extraction techniques, to try to look into report official reports and other data set. I might have some really information like flammable gas. It's not necessarily like writing that type of thing or something else to get some clue.
All right, wonderful. Thank you, Melissa. All right, thank you, everyone. Today has been a really great day. For us in government, it's vital that we stay connected with industry to understand your challenges and your opportunities so that we can ensure our data, programs, and support truly help drive discovery and innovation in Queensland. I would now like to ask Janelle back up to the stage for the student awards and closing remarks. terrible as they're a bag of rock. People actually do that, so most places that good terrible fries. So I'm gonna put this on its head a little bit. I'm gonna save the student prizes to the end because I think they're one of the most important parts of a day like this. For me, seeing the energy and enthusiasm of the next wave of geoscientists, geochemists, engineers, researchers of all disciplines who are interested in participating in the mining industry is one of the great highlights for me. I'm going to save them to the end because I think it's a wonderful highlight to end on. So if I can just reflect back to people what we've seen through today, and I will be quick, I promise. I know we're a little bit over time, so I've stolen some of your minutes already. I'll steal a few more. I started today by talking about the 6 ways that we as GSQ support the industry. And I hope what I can convince you over the next couple of minutes is you've seen a great spread of that today. So the 2 presentations you've just seen from the SMI and CSIRO are 2 projects that we're embarking on as GSQ, collaboratively with external partners to generate that knowledge that feeds into our advice portfolio. So understanding what are the limitations of copper production in the northwest. Is there a potential in Queensland for natural hydrogen accumulations? These are key bits of information that we as GSQ feed through to our policymakers to change our regulations if required, or change the way that we're thinking about supporting the industry. There's your advice piece. If I think about our data systems, obviously Mark got up and talked about how our data systems might need to be positioned to enable future technologies to use the legacy data that we've already got in those systems. So there are data systems piece. Next up, we have pre-competitive geoscience data generated through our programs, all through collaborations with Geoscience Australia. So you saw in Ladina's presentation, in Matt's presentation, in Dominic's presentation, the new data that we're generating for use directly by explorers. And then if I think about our legacy rock collection at the EDCs, that was the foundation for the work presented by Roger, by Elena, by Vlad, generating not just data, but also knowledge and insight for our explorers to use in their exploration. The only thing that you didn't see on this stage was our funding programs. I hope that anyone interested in those found Heather, who's been on stage all day, helping guide us through. Courtney, Sonia, to have a conversation about those opportunities. We don't think we need to screen those ones from the rooftops. We think we need to have targeted conversations to prompt people to put in the best programs that they can. So, hope you see that what we've tried to do is weave together a day that shows you the broad range of things that we're doing in GSQ. I have some thank yous before I get on to the very exciting awards. First to Heather, I cannot think of a better MC. Your energy buoyed the whole room through those post-sleep crashes. For enthusiasm is infectious. Thank you for all the hard work you put in to be the MC today. To Matt and Roger, who have been making sure the tech works behind the scenes, thank you very much. Appreciate it, doesn't go unnoticed. Without them, there would be no recordings of this, so you would only be able to know this if you were in the room today. Thankfully, we can share it more broadly after the event with the recordings. Lydia, Angela, Griselda, and Amy, who have been instrumental behind the scenes, not to tell you how much work these ladies have done putting on this event, everything from catering to room booking to the reception desk, to making sure the day flows properly. The work that they do hugely important, and this event would not happen without them. So thank you. I think that's it. Yeah, I haven't missed anything that Heather is going to yell at me about. So thank you to everyone who voted for the post-its. I appreciate you taking the time to review some wonderful work that was conducted. We have some very attractive core samples. Got our student poster. In third place, we have the poster Cobalt and Nickel Enrichments in Sulphide from scar-hosted ISCG Mount Colin deposit, concrete deposit, from Gabrielle. Congratulations. In second place, the poster titled Alteration, Pyrogenesis and Trace Element Geochemistry of Sulfides from a Land RFD, Copper, Novel and Rare Earth Started Logic. Do you need a picture? Thank you. And I have to say, this is a very beautiful piece of coal. I think Elvis might have picked these pieces of coal, so if you want to know what they are, I would suggest you go to that map. All from Mount Morgan. Beautiful piece of Mount Morgan coal. Our first prize winner was the poster titled Turning Pyrite into Pyrrhotite via High Temperature Calcination. I love that our award winners come to the front afterwards, so we can take a photo if you're happy with that. Thank you. That's it from me. Thank you everyone again for coming. I appreciate this, especially who have travelled. Hope you got a lot out of today. We will send you a feedback form, so if you quite hated today, you feel free to write that in the feedback. I think I will hand over to Heather. Thank you.
Alrighty, thank you, everybody. This has been such a great day. I'm glad to see there are still so many people here. If you want to continue the conversation like I do, head down to the Port Office Hotel where AMEC are hosting free drinks. Everyone's welcome, even if you didn't get a chance to register. That's okay, they're expecting us. So looking forward to seeing all of you at Digging Deeper 2026. Thank you.